Okay, so now I want to start addressing the safety life cycle. Inside the standard, the steps that you have to follow to analyze your system, design your system, validate your system are defined into the safety life cycle. So we start defining what the item shall do. This is the item definition. Then we have to analyze the hazards that could impair the item in working correctly. And we have to understand which is the risk associated with those hazards. Out of this analysis, we can eventually define the function safety concept. So what's the rationale here? First, we understand what the item shall do. Then we understand what can go wrong when using the item. And at the end, we define the specification of which are the additional functionalities to mitigate the risk. We know that something goes wrong. What can we do to take countermeasures against the hazard in such a way that even if we have a misbehavior, it will not harm the driver? Think about the ABS. The ABS is able to work in different modes. There is the full mode, where the ABS is able to measure the speed of the wheels by reading through 4 independent sensors the rotational speed of each of them. Then based on this and knowing the speed of the vehicle as received by another system inside the vehicle, is able to understand whether there is a wheel that is losing friction. If this is the case, the ABS is able to cut the braking pressure on the hydraulic circuit of the different 4 wheels independently in such a way that the wheel that is blocked due to the sudden brake starts rotating again to gain again traction on the road. If there is a problem with the communication channel that provides the speed of the vehicle, the ABS is not able to operate correctly. But in order to continue to provide service to the driver, the ABS will work in a degraded mode. So somebody recognizes that the fault can happen, which is the functionality that is activated when we are not able to provide the full functionality. Is a degraded mode, according to which the ABS works on either the 2 front wheels, on the 2 back wheels, producing the same corrective action. So we have the full mode, full operational mode, that is the one that is used when everything is working correctly. Then we have another mode that is a degraded mode that is used as a complement to the full mode when a fault has been recognized. Last stage is that when we have a failure on one of the sensors on the wheel, we give the driver the information ABS not working, please be careful. This is the last resort. We can do nothing there. If the sensors that we need to operate are not there, we can do nothing. But the only thing that we can do is to say to the driver, please be careful. ABS is not there to help you. Okay? This is a way for informing the driver that the ABS is not there to help him or her. This way, we hope that the driver will take the proper, say, action to manage this scenario. Typically, it will reduce the speed. He or she will not brake suddenly. Okay? So this is part of the concept phase. We understand what the item shall do. We understand what can go wrong. We define countermeasures. At the end of this step, we defined specifications. So we are not designing nothing here yet. We are just saying what we want to have in terms of functionalities. Once the specification is done, we can move towards the product development. And this is done in different steps. First, we have a system-level view of our item. So we know that we have to reach some goals in terms of additional functionalities. How we do that? Do we do everything in hardware? Do we do something in software? We do everything in software? These are system-level decisions. We have to decide how to partition the system. This is going to be done in hardware with this additional functionality. This is going to be done in software with this additional functionality. That will be obtained off the shelf because we will adopt a certain hardware component that will provide us some functionality oriented towards safety. Then once the system level analysis has been done, the system level design has been done, we can move forward towards the hardware implementation and the software implementation. And these are part 5 and 6 of the standard. Here we will have to put at work a number of practice to validate that the specification has been satisfied. So we specify a certain goal, we implement, and then we validate whether the result of the design is consistent with the goal that was specified. If yes, we are ready for production. And at the end, when we produce the item, we can ship the item to our customers. Okay? This is the overall flow. So where as engineers you can be involved? For sure, you can be involved in this first part. So in the concept phase, if you are going to work as an engineer in an OEM, normally if you go at the GM or FCA, you are there to specify something. This is because the OEM normally has a system level understanding of the application. So you see the whole engine, you see the whole vehicle. So there you specify the functionality. So you tell what you want to achieve. You analyze your system and you define the functional safety concepts. So what you want to achieve from your system in terms of nominal functionality and redundant functionality added there for functional safety. Then you could also have the role of designer. This is typically the case if you have a background in control, where you have the capability of specifying or designing the control algorithm, the exhaust gas recycle valve control algorithm, the control law for the combustion of your engine, the control law for the active suspension. So you can be asked to implement the skyhook controller for keeping the proper level of the chassis of your vehicle through direct control of the suspension of the vehicle, and so on and so forth. If you are hired by a tier 1 company like Magneti Marelli, Tier W, Denso, Bosch, Continental, Delphi, and plenty others, you can be involved here in the system level design if you have a senior knowledge, so after 5 years that you are hiring the company, or if you are junior, you will be involved in the hardware level design or software level design. So So you see just one component of the overall system, of the overall item. Then you will be likely involved in the validation testing and validation phase of this hardware and level and software components, and possibly you will be involved in the validation and testing of the integration of the software on the hardware. Then the tier 1 ships the result of the design activity to the customer, so to the OEM. Again, if you are in the OEM, you can be involved in the validation phase at the system level. So you have the electronic control unit designed by Bosch, you receive it, you connect it with the real engine, the real gearbox, or let me say a proper model of the plant you want to control, and you validate whether everything is working fine. You validate whether the engine is behaving correctly, the diagnosis is behaving correctly. You validate whether if the fault happened, the proper action as you specified is implemented. These are the typical jobs that you can be involved in. If you are very unlucky, you will go selling something. Could be services, products, or whatever. Okay, so this is an explanation of what I just said. Let me start now addressing the concept phase. So here we will start looking into practical things. So this is something that we have to learn to put at work. So the concept phase, we will start it with the item definition. So let's imagine we are willing to design a new vehicle. We are willing to put there a new electronic system. We have first to conceive what that electronic system is intended for, what the item is going to do, which is the functionality that the item is going to provide, which are the elements of the item. Do we need a CPU with a memory, with I/O, with particular sensor, or we are just looking into an electronic system with CPU and memory and nothing else? Which are the elements that belongs to our item? This is very important because once we know which are the elements of the item, we know what can be broken. Based on that, we know what we have to do in terms of analysis of the misbehavior that could happen. And based on that, we can take the proper countermeasures. Then we have to understand which are the functionalities that we are requiring from other items. ABS contains sensors for reading the wheel of the speeds, the speed of the wheels. Then it must receive from a suitable network, the CAN network of the vehicle, the speed of the vehicle. So somebody else should provide the speed of the vehicle. This is a functionality that our item is demanding to somebody else. So we need to understand the interactions. This is because also the interactions can be broken. So what happens if we do not receive the speed of the vehicle, or what happens if in the last half a second we always receive the same speed? This could be an indication that something is going wrong. So we have to understand what is inside our item. Let's imagine that with the item definition, we define a perimeter. Everything that is inside the peripheral of this perimeter is of our concern. We have to look at it closely. Everything that is outside, we don't care. It's not our business. Okay? Then, we can now start the hazard analysis and risk assessment. The goal here is to identify and categorize the hazards that could come from malfunctioning of the item. This is difficult because you have to understand what can go wrong, when this can go wrong. and which could be the impact on the driver, on the passengers, or on the other people around the car that host our item. This is something that we haven't yet analyzed, but it is worth saying now. Remember that the item cannot work properly and somebody can get hurt. But we do not have to consider only the people inside the car. We can have people around the car. Think about a system that helps you in parking your car, like the distance sensor that you can have on the back bumper to inform you which is the distance towards the nearest object that you cannot see on the rear mirror. This is typical of modern cars. Okay. So that radar measures the distance using ultrasonic sensor of the nearest object. The object can be a kid that is not tall enough to be seen in the mirror. What happens if you drive backwards, relying on the sensor is broken, it doesn't tell you that there is a kid on the back of your car, and then you hurt the kid while driving. Okay? This is the kind of analysis that you have to do. And remember, you don't have to consider only the people inside the car. There could be people around the car. And they have to be considered as well. The definition of hazard is, of harm, is the injury to people due to the malfunctioning of the item. It doesn't say people seated inside the car. Okay? Then, once we analyze the risks, we categorize the risk, we have to formulate safety goals. This is to say, we have to specify which are the functionality that we want to have out of our system to enforce safety, so to avoid that somebody is killed. The steps that we have to go through are the following. We do first situational analysis. Then we do hazard identification and classification. We do ASIL determination and safety goal determination. So let's go through these steps. The situational analysis has the purpose of describing the driving scenarios The situational analysis has the purpose of defining the operational situation, that is the driving scenarios where we are using our item. This is because that are the conditions that could end up in a risk for the user if the service of the item is requested and it is not delivered. Here, there is no golden rule to identify the different scenarios. We have to do brainstorming. There is no maths here to be done. So there is not a formula that tells us which are the exit driving scenarios. We have to do brainstorming. Here, teamwork is important. You have to sit around the table with all the people involved in design of the item and the application for which the item has to be used, and you have to do brainstorming there. Example of the result of this brainstorming is driving at low speed, or driving at high speed on icy road, or being in an incident condition, driving backwards at 30 kilometers per hour max. These are the kind of operational situation they are interesting for us. Okay? Then we have to do hazard identification. Once we know which are the elements of the item, we can understand which is the implication of a fault in each element of this item. and through deduction, brainstorming, FME analysis, we can guess which is the event, the hazardous event associated with the fault. Let's say we have an ultrasonic sensor to measure the distance of the nearest object. We have a fault in this ultrasonic sensor. What could be the fault? We could have, for example, no reading. We are not able to measure the distance. Or we can have a false value. Let's say the reading is corresponding to a distance higher than what it actually is, or lower than what it actually is. In terms of the function that the item shall provide, which is the effect of this? If we were using the ultrasonic sensor as a radar, having no distance, it's a problem for sure. We cannot provide any measurement. Having a false distance that is considered higher than what it actually is a very big problem, because you are assuming the object is much more distant than what it actually is. If you have the opposite, the object is more distant than what you are thinking of. This could not be a problem. It is conservative. Okay? This is the kind of analysis that you have to do. Again, no golden rule here. You have to do analysis, brainstorming, discussions, and at the end, you have to come up with a list of hazards. Then we have the hazard classification. So we know which are the operational situations. We know which are the hazards that could happen in those operational situations, which is the outcome. So how severe is the damage that results from the harm in that, from the hazard in that operational situation? Then which is the exposure? So how likely it is that we are in that operational situation when the failure happens? And then which is the controllability? So if the item is not belonging as expected, we are in the driving situation, the fault is active, that is, we need to have the item, but the item is not providing the service as expected, how much likely it is that we can control the scenario? These are things that we have to quantify. This is to be done, again, based on experience. There are some, I would say, rule of thumbs that will drive us in defining the severity, exposure, and controllability level. For each of these, this rule of thumb will provide us a number. This number tells how severe the hazard is, how likely the exposure is, how controllable the hazardous event is. Here is a description of the different parameters that we have to consider. So we said that the severity is the measure of the extent of the harm to individual. The scale we are using is this one. 0 means no injuries. We have the accident, nothing suffer anything. Then we have light and moderate injuries. So we have, for example, a scratch on our forehead. We have severe and life-threatening injuries, but the survivability of the people involved is likely. And then we have S3, life-threatening injuries, survival uncertain, or fatal injuries. Where does this come from? Simply from record of accidents. Every year we have millions of accidents worldwide. They have been closely analyzed. So the different possible injuries are very well known. And it is possible to derive these categories. Similarly, we have the controllability. As we said, the controllability is a measure of the capability of avoiding a specific harm due to the timely reaction of person involved. This is a way for capturing the fact that in the hazardous event, there is a person in the loop. A person could be able to react. Okay? Which is the capability of reacting. It depends on the event that is happening. The scale is the following. We have C0 when the event is controllable in general, C1 when it is simply controllable, C2 when it is normally controllable, and eventually we have difficult to control or uncontrollable. We will see later on how we can tell which is the best value there, given the operational situation, the hazard we are considering. For the moment, let me just explain you the different categories, show you the different categories. And then we have the exposure. The exposure is a measure of being in an operational situation that can be hazardous if coincident with the failure. Again, we have the categories from 0, incredible, to 4, highly probable. Example of incredible. You are getting hurt if you are driving while an object from space hits your car. It's a meteor that is hitting you while you are driving. This is incredible. You are laughing, but it happened. 1 week ago, no, 1 month ago, more or less, there was a news on the newspapers about a person, I don't remember which is the country, it could be India or could be Far East in general, that has been killed by an object falling from the space. So a micrometeor hit the ground and killed the person. So this is very unlikely. I would say it's incredible, but it could happen. High probability. The fault is of concern every time you ignite your car. Well, this is very probable. Every time you use the car, you turn it on. So it is very probable. Okay? And then we have, let's say, shadows in between. We will see which are the rule of thumb to derive this value. So don't forget the big picture. What we have to do here? We define the operational situation, we define hazards, we rank each hazard in terms of severity, exposure, controllability. Then we aggregate this into ASIL, so automotive safety integrity level. How this integration is done? Well, the result will be from QM to D, and the aggregation is done through this table. So the table tells us which is the ASIL that we have to consider for a certain item, for a certain operational situation, when a certain hazard happens, based on severity, exposure, and controllability. So let's say severity 1, very light injuries. Exposure 1, very low probable. Controllability 1, very controllable. The fault is just a measure of quality. We can neglect it. Okay? If the item is faulty, and that particular hazard happens when we are driving, we are using the item, we just have a bad feedback about the quality of the product we are using. This is a budget car. Next time I change the car, I will change the brand. That is the typical reaction. Okay? If we move forward, we can see how the ASIL could increase. Severity 1, very light injuries, but this is something that happens very often, exposure 4, and when it happens, it's not controllable. Well, this is ASIL B, but it's already in the middle of the criticalities, but this is something that we have to take care of. We can't just say, oh, don't care, it's just quality measure. No, this is something that has an impact on the driver. The driver gets hurt, lightly hurt, but much more often than what is acceptable. It is happening very often, E4. So it's like every time you brake your car, you do like this with your forehead and you hit the steering wheel. This is not acceptable, okay? It's a light, very moderate harm, but it is happening every time you drive the car. Not good. So we have to take care of it. Then if we go down to the extreme scenario, S3, somebody dies here. E4, highly probable, uncontrollable, D. Think about unintended acceleration. This is something that could happen when the chain of events that we have seen happens. So if you are in the driving situation when the fault happens, there will be harm, and the harm is very probable. So every time we drive, we could have the unintended acceleration. So very probable. It is uncontrollable. Remember the scenario. We have either to power off and power on again the car, or switch to neutral to come out of that hazard. Very difficult to put at work that condition when you are stressed and scared about what it is happening. So C3. Then S3. If that happens, you will die. Very likely. So this is D. Very critical. Okay? Is this clear? As you can see here, the distribution of A, B, C is, let's say, a mix of how severe the injury is, how probable how high or low the exposure is, and how controllable the situation is. Up to the point that even if the hazard can be very severe, because we have S3, but it is very unlikely, and it is very well controllable, then it is QM. Okay? So it is not so straightforward to derive the ASIL. This is something where you have to spend a good deal of time. If you don't do this analysis carefully, you will end up in two scenarios. First scenario, you will consider your item much more dangerous than what it actually is. So you will put at work a very long number of techniques to be compliant with the ISO26262, for example, for designing versus ASIL D. The end result of your product will be very safe, much more safer than what it is actually needed. This could be positive, but on the downside, your item will be much more expensive than what it could be. And this is very bad. Remember that in automotive, the number of items that you produce are so high that saving 1 cent could make a big difference. Okay? If you have to design for ASIL D, you have to pay much more than 1 cent for each item. And this could be really a pain. You can have a very bad outcome of your design activities in terms of budget and cost and profits. So this is something that we want to avoid. The other hand, if you do this too light-hearted, you will end up, for example, with an ASIL B when a C is needed. So you will under-design your item. And this is very bad again, because you will not be able to provide absence of unreasonable risk. So your item will be dangerous for the user. You will risk of injuring somebody by deploying that item in a vehicle. And somebody will ask to you to pay for this, because if somebody is hurted, there could be a trial, and the OEM can be forced to pay by a judge. If you are the supplier of the OEM will come to you, say, oh, you haven't done the proper work, so you have to pay. I'm not going to pay for your faults. Okay? This is the chain of events that could happen. So again, over-design is not good from the profit point of view. Under-design is not good from the safety point of view. But everything depends on the result of the hazard analysis and risk assessment. So this is something that should be done very carefully. Then, once you are done with the hazard analysis and risk assessment, well, it is time for defining the safety goal. For each combination of operational situation and hazard that is not QM, you have to specify a safety goal. So you have to tell what the item has to do to provide safety against that hazard in that operational situation. So the goal is the specification of what we want to have from the item in response to that hazard to avoid harming somebody in that specific operational situation. The goal is fulfilled through functional safety concept. The functional safety concept is the functional specification, so the additional functionality we want to employ to reach the safety goal. We will see this in detail through an example. Let me do this. Let me start looking into an example, because I think this is needed for catching all the different concepts that we have seen today. Here, today we analyzed the concept phase. We already have seen a lot of important concepts. We need to, let me say, digest these concepts by putting things at work. So today I'm going to show you an example. Probably we will not have enough time for finishing this, so we'll go ahead next week. And then I have prepared a couple of other examples for us to work on, so that we will try to do some, let me say, class work to settle down these concepts, okay? So let's imagine we want to deal with this system. This is a cross-traffic car system. What's the purpose of this system? So let's imagine that on the two back sides of your car, you have radars. These are intended for measuring the speed and the distance of approaching vehicles or obstacles when you are driving backwards. What's the idea? You may have a car with a reduced visibility, or you can have, or you want to increase the awareness of the driver when doing maneuvers like this one, so exit backwards from a parking lot. So you can have this electronic system that alerts you that an object is coming towards the vehicle. Okay? So this is part of the active driver assist systems that are more and more often deployed in newer vehicles. So if we want to have a conceptual view of this item, we can see that it is composed as it is described here. So we have a rear left rudder, we have a rear right rudder. These are connected in some way with a microcontroller. And then we could have some IOs of this microcontroller towards the rest of the vehicle. For example, we can have, through the vehicle network, the information about which is the current gear, so that only if we are driving backwards, it is important to activate the service of this system. And then we can have, for example, as output, let me say, the command to turn on or off a lamp on the dashboard of your car to give you to give the driver the visual indication of where the vehicle is approaching from and which is the speed of the vehicle or which is the distance of the vehicle. So let's imagine this is the driving scenario. You are seated in the car here. You are driving backwards. There is another vehicle approaching you. And then on the dashboard of your car, so right in front of the steering wheel, you have a lamp like this one that is turned on to say that there is a car approaching from the left. And for example, we can imagine that the blinking of this, the blinking rate of this LED is proportional to the distance of the car. Okay? Obviously, if the car is approaching the other way, we could have another icon that is another LED blinking on the other side of the dashboard. Okay? That's the purpose. Then we have to do the hazard analysis of this. So first we have to identify the items. Which are the elements of the item? Well, we have the microcontroller. Everything is software driven, so we need to have something to run the software. So we need to have the microcontroller. Typically, we don't have a microprocessor here. Instead, we have a microcontroller. Which is the difference? Well, simply speaking, the microcontroller is a microprocessor plus the memory plus all the other IOs that are needed to run an embedded system all in a single chip. Okay? So when you see microcontroller, think about a computer that is processor, memory, IOs, everything integrated in a single chip. Okay? Then we have the left rudder and the right rudder. This is the perimeter. We have to analyze the system considering those elements. In other scenarios, we could have only the microcontroller because, for example, the radars are part of another item that is providing the distance of the approaching obstacle through the vehicle network. Could be the case. It depends on the architecture of your item. So as I said, here we draw a perimeter. In my perimeter, we have microcontroller, radar on the left and radar on the right. We have to analyze what is going wrong when each of these is broken. In the other scenario, we could have a perimeter that contains only the microcontroller. The radars are left outside. This is something that you know in advance, because you will be the designer of this item. So you decide, depending on the architecture of the vehicle where this item shall be deployed, what is inside the perimeter, what is outside. Okay? And once you define this perimeter, all the rest that you have to do is analyzing the hazard that could happen on those elements of the item in the different driving scenarios that are worth of being considered. Then, which are the interactions that we have? Well, we have for sure an interaction with the element inside the computer, inside the car, sorry, that is responsible for providing the current gear. This is typically the body computer, an item inside every vehicle that is a kind of gateway. It is where you run the commands for turning on and off the lights of the car, that is responsible for distributing in the vehicle informations like the speed of the vehicle. It is where you connect the commands that you have on the dashboard and on the steering wheel. Think about the different levers that you have on the steering wheel. Think about the push button that you can have on the dashboard. All of them are handled by the body computer. One of the things that the body computer delivers is the speed of the vehicle and the gear of the vehicle. Then, which are the functionalities that you provide? Well, you provide the PWM to control the turning on and off frequency of the visual indication of the approaching obstacle. This functionality is provided to the vehicle, but you need to have a consumer of that functionality. So who is the responsible for turning on the warning lamp? Well, this is the functionality that the item is requiring to other items. In this case, we are requiring the body computer to provide the current gear and to turn on and off the warning LEDs. So here we define the perimeter, we define the functionalities. Now, let's have a look at the operational situations. What could we have? Well, I think that for the sake of simplicity, we can consider these few scenarios. Let me try to explain them. We have an obvious operational situation that is the car driving backwards. If the drive is driving forward, who cares? The item function does not apply. So we take into consideration only the vehicle driving backwards. Then here, I think we have to take into account, let's say, two elements. The first one is the visibility. This cross-traffic assist helped me in looking for obstacles that could hit the car. But I could have, as I always had before cross-traffic assist, the capability of recognizing whether there is an obstacle or not. I just have to turn the head and look backwards, okay? This is what you do when you drive. So, and then we have to consider the visibility. Here we can have a good visibility, like in this case, we are parked here and we have an empty parking lot beside us. Or we can have reduced visibility, because we could have another vehicle parked beside us. You go to the group store on Sunday morning, 10 o'clock. You are in this case. Nobody is parked in that big parking lot. Okay? You go there on Saturday, 4 o'clock. You are in this scenario. It's very crowded. Okay? So this is something that happens. It just depends on when you use the car. Okay? Then, the second element that you have to consider is who is approaching you. It could be a vehicle like this, or it can be a bicycle or a motorcycle. It makes a difference. Because remember that the person that could get hurt is the person inside the vehicle that hosts your item, but also other person around this vehicle. So as you can easily imagine, if the incoming obstacle is a vehicle, like this one, so another car, you can have an incident, but the person here is inside a big metallic vehicle. If you have an incident with a bicycle, or a pedestrian, or a motorcycle, it's a different story, because the person involved doesn't have the level of protection that you can find within a full car. Okay? So you have, in this case, you have to consider 4 operational situations. Vehicle exiting from empty parking lot, vehicle approaching, operational situation 1. Operational situation 2, vehicle exiting from full parking lot, vehicle approaching. Then the same, but instead of having a vehicle approaching, we have a cycle approaching. So vehicle exiting from empty parking lot, cycle approaching. Vehicle exiting from full parking lot, cycle approaching. Okay? Is this clear? You may wonder what does it change. We will see in a minute. Okay? Yes, please.
In theory, we could have an infinite number of operational situations,
So the question is, can we have an infinite number of operational situations? The answer obviously is no. You can't have an infinite number, otherwise you will not be able to treat all of them. You have to consider only the operational situation where the item applies. Okay? You could have written here, driving forward at low speed on an empty road, driving at high speed on a crowded road. This is a rather valid operational situation. But the question is, does the item apply in those operational situations? So you can have the item that starts working giving you false indication of an approaching vehicle on the back when you are driving forward on an empty road. This is QM for sure, because nobody gets hurt by that kind of failure.
Why a bicycle, not a pedestrian or a child?
What? Your question is, why do we consider just a vehicle like this and a bicycle like this, not a pedestrian, not a child? Well, you're right. You could consider each of these cases, but they are finite. What do you have here? You could have a passenger car or a heavy or a moderate duty vehicle. Okay? Or you could have a motorcycle, you could have a bicycle, or you could have a pedestrian. They are not infinite. Okay? So in theory, when you go doing this work, the real life, you have to consider all these scenarios. They are finite. They are more than the one that I have considered. But for the sake of this presentation, this is enough. Okay? Any other question? Okay, so let's imagine that this is enough. Then, which are the hazards that we have to take care of? There are many ways of doing things. You can have the negation of the provided functionality, that is, the item does not provide the functionality when required, or the item provides the functionality when not required. This is a very simple approach. Or you can have a more structured approach. Let's say that the first approach can be useful when you have no idea of what is inside the system. So you have a very rough understanding of which are the elements of the item. You have no clear idea of what is really inside your item. And so the only thing that you can do is to be very, very abstract with respect to the items of your system. You cannot make any assumption. If you have a more detailed knowledge of what could be inside your system, because maybe you are redesigning an already existing system, so you are leveraging some previous design experience, you can use a more structured approach like the failure mode effects analysis. What's the idea here? Well, first you have to consider all the elements of the item. For each of them, you have to consider the possible failure modes. So how the different element can get broken. For each of these failure mode, you have to infer which is the effect on the functionality the item provides. This will give you the hazard. Let me give you an example. Let's imagine we are considering the right sensor. The sensor can be subject to 3 failure modes. The first one is no distance measurement. The sensor is unresponsive. This is because we have a broken wire. This is because we have a broken sensor. Let's imagine that somebody hit you from the back and broke the sensor that is inserted in the side of your bumper. Well, the sensor is broken. It is not able to provide any distance measurement. Then another failure mode is wrong distance measurement. The actual distance is higher than what measured. Okay, you have a broken, or you have, you could have a part of your sensor that is broken in such a way that you measure 10 meters, but the object is 15 meters, okay? The last example is you have the wrong distance measurements, but the actual distance is smaller than what measured. So you measure 10 meters, but the object is at 5 meters, okay? These are the 3 possible failure modes. Unresponsive sensor, faulty sensor, let's say more pessimistic than what reality is, and more optimistic than what reality is. So this is just one failure mode. What is the effect of that failure mode on the item? So which is the hazard associated to that failure mode? Well, in the first case, the item does not report any obstacle. The sensor is broken. So we do not have the capability of recognizing an obstacle. So even if the obstacle is there, the item says no obstacle. Okay? For the second failure mode, the situation is the following. The item reports that there is an obstacle there, and the item says that the obstacle is closer than what it actually is. We have wrong measurements. We say it is 10 meters, instead it is 15. So the item, based on the measurement, warns us as the object is closer than what it actually is. The last one, well, the last case, it is the opposite. The item reports the obstacle more distant than what it actually is. Okay? So let's imagine that you are driving backwards. You are relying on this visual indication, and the indication says, oh, 10 meters from now, you have an obstacle. You may consider that you are able to complete your maneuver before the obstacle is close enough to have an incident. But in reality, the obstacle is just 5 meters. So you don't have enough time to complete the maneuver. The correct action should be stop the car to avoid hitting in the obstacle. But you are not able to do that because the sensor is faulty. Okay? So this is the meaning of this hazard. Is this clear? For the left sensor, the same applies. So let's imagine here we have just considered the case of obstacle approaching on one side, but we could have also the same from the other side. Okay, so the same conclusion comes from the analysis of the left sensor. Then we said that we have a microcontroller in our system. let's imagine that the microcontroller fails in executing our software. So the item does not report any obstacle. The sensor is fine, but the microprocessor is broken. We are not able to run the software. So we are not able to inform the driver that somebody is approaching. This is the failure mode. This is the hazard. But the network fails. So our item that is requesting some functionality to inform the driver about the incoming obstacle delivered by another item is not able to communicate because the network that connects the item with the other one is broken. So the item does not report any obstacle. Okay? Any doubt, question so far? Okay. So here we identified the hazards. We identified the operational situation. We have to put them in a matrix. So for each operational situation and for each hazard, we have to guess severity, exposure, and controllability. Okay? So this is what we have. Operational situation 1 and 2, hazards 1 to 3. Operational situation 3 and 4, hazard 1, 3. Okay? Then let's start looking into the severity. The severity is a measure of the potential harm to person. To person. We don't care if another item is broken out of a hazard happening in a certain operational situation. We don't care if we have a new scratch on the side of the vehicle. Who cares? What that is relevant for us are the persons. The persons could be the driver, the passenger, the pedestrian, the cyclist, the passengers of other vehicles, the driver of other vehicles. Those are the persons that are important for us. Okay? So, how to measure the severity? Well, based on the databases of previous incidents, we can have this rule of thumb about the severity. We consider the speed at which the incident occurs. If the difference of speed between the two vehicles is less than 20 km per hour, then we have severity 1. If the difference is between 20 and 40 km per hour, it is S2. If it is above 40 km per hour, it is S3. This is what we have if the collision happens between two cars. If the collision depends between one car and a bicycle, a motorcycle, or a pedestrian, we have to increase the severity. That is, it is more likely for the pedestrian or the bicycle or the cyclist to be severely hurted than the occupant of another vehicle. So let's say that if the incident takes place between a vehicle and a cyclist, we have S2 when the incident takes place in a built-up area, like the parking lot of a city. This is because normally the speed of the vehicle is low, and so the energy of the impact is lower. If the incident between the vehicle and the cyclist happens outside the city, roughly speaking, as the speed of the vehicle is higher, well, the energy is higher, and so most likely the impact will result in a S3. Okay. This is again a rule of thumb. If we consider Torino, if we consider Corso Duca degli Abruzzi, we consider what cars are normally doing, moving from one traffic light to the other one, they can go up to 70 or 80 kilometers per hour. So if you have an incident there, well, it is still within a city, but the speed is high. And so it is most likely that if the person, like a pedestrian, is involved, it will be S3. Okay? Is this clear? So don't take this as written in the stone. Put always the scenario in the proper context. If it is inside the city but at high speed, the severity is higher. If it is outside the city but at low speed, the severity is lower. Okay? Then, for this, we can have, following this consideration, we can have this result. So basically we say, for all the operational situation, OS1, OS2, no matter which is the hazard, we have, well, wherever we have hazard 1, we have severity 1. This is because we have a crash between two vehicles at low speed. We are doing maneuver inside the parking lot. We are going slow. We have two cars that hit each other, so severity is 1. Okay? Then, if we consider H2, that is the sensor is faulty, gives me a false indication of the distance that is higher, that is lower than the actual distance, it means that the driver will stop the car, even if it is not necessary. Vehicle coming towards you at 5 meters, stop the car. Let it pass by, and then we resume going backwards. Okay? So it is very likely that you avoid the incident. So the severity will be 0. We have no incident there. In case of H3, it's a different story. We say, oh, incoming obstacle, incoming car at 10 meters. Okay, let's do the maneuver. But it is just at 5, so we can have the impact. In this case, it is an impact at low speed, so severity will be 1. Okay? When we consider the other scenario, so 3 and 4, here we have a cyclist involved. So take into account that we are in a parking lot. So it is likely that we are driving at low speed. Most likely we just have S2. We can say S2 for H1 and H3, while for H2 the same consideration as before applies. We stop the car because we think that the obstacle is much closer than what it actually is. Okay? Is this clear? Any doubt? Okay. Then let's look at the exposure. The exposure is a bit trickier. The exposure is a measure of how likely it is in the operational situation when the hazard happens. It is difficult to give you a way for taking this decision. It really depends on the operational situation, and there are different ways of formulating the exposure. Well, first of all, let's try to understand the meaning behind E1, E2, 3, and 4. Let's consider E1. E1 says possible but very low probable. But what does it mean, low probable? Well, we say that an event is low probable if the probability is below 0.1%. Whatever is the way in which we define the probability, if the probability is below 0.1%, the event is low probable. Okay? E2 is 10 times more, so 1%. E3 is 10 times more than E2, so 10%. E4 is more than 10%. Okay? Whatever is the metric that we use to define the probability, these are the threshold. Okay? Then let's see how we can define this metric. Well, the metric can be defined basically using the percentage of operating time, the frequency of occurrence, or the mean time to situation. We will look only at the first two. The percentage of operating time is a ratio between the time for which you are in the operational situation divided by the total amount of time for which you are using your vehicle. Example, let's imagine that the operational situation is power sliding doors open while traveling at high speed. Okay. So which is the exposure here? So, sorry, this is the this is the combination of hazard and operational situation. The operational situation is traveling at high speed. The hazard is power sliding door opens. Okay. So let's imagine that we have a vehicle with electric doors. So the door is controlled by an electronic control unit. You can have a failure such that the doors open while you are traveling. That is the hazard. The situation is traveling at high speed. So we have to tell which is the exposure of traveling at high speed. So here we have to consider which is the driving scenario, for how long we are driving our car, and then we have to consider for how long is the time for which we are traveling at high speed. The ratio between the two gives us the exposure. And these are examples of exposure based on the operational situation. Example, we are traveling on a highway and there is a lost cargo or obstacle on the road. Or we have a vehicle in front of us during a jump start. This is low probable. It's very low probable, sorry. Then let's imagine that we are overtaking, or we are exiting the highway, or we are crossing a road. Well, this is maybe low probable, because it is not granted that every time you drive you do an overtaking. It is not always the case that every time you drive on the highway and you take the exit on that highway. Example of high probability, so high exposure is accelerating, braking, steering, parking, driving on highways. But these are more probable. Every time you use the car, you accelerate. Every time you use the car, you brake. So if the operational situation is accelerating, braking, the associated exposure is very high. Okay? Is this clear? The frequency of occurrence is another way of thinking to exposure. Is when you answer to questions like how many days per year the snow and ice is encountered. Let's imagine that the operational situation is I am building an item to be deployed in a vehicle for the Northern Europe market. So my vehicle shall be sold in Sweden, Finland, Norway. So probably the exposure to an operational situation driving on snowy or icy road would be very high. Let's imagine that the same vehicle equipped with the same item shall be sold in North Africa. Probably the exposure to the operational situation, snow and ice on the road, will be very low. Okay? So it depends on what the item is intended for. It depends on where this will be deployed. It depends on the operational situation to tell which is the exposure. Another example is how often the car is started every time. So here we are considering how frequent the operational situation is. And again, here we have example. E4 is for starting the car, shifting the gear, accelerating, braking, steering, using indicators, parking. These are actions that you do every time you ride the car. You drive the car. So if the operational situation is one of these, the exposure will be high. Okay? This we can skip. So for what we have seen, we can say that for our operational situations, the exposure is very high. We are driving out of a parking lot. This is happening each time we drive the car. When we drive the car, we reach somewhere, we park it. And then we have to exit the parking lot. Then maybe you can refine a little bit this, saying, but it's not always the case that I am parking in a parking lot like that one. I can park also alongside the road, parallel to the road. Okay? But I think that in any case, whenever we use the car, we park it. So the exposure here is very high. Then controllability. The controllability is an estimation of the probability that the driver or the person that could be endangered by an incident are able to avoid the harm, by promptly reacting to the hazard. The assumption we do here is that the driver is in normal condition, so it is not exhaustive, not drunk, and so on and so forth. Is behaving, let me say, according to the regulation or almost according to the regulation, so he's not a pirate, and it is and he or she is trained, so there is a driving license. So the controllability for the driver depends on the possibility and capability of the driver to perceive the critical situation and the capability to put at work promptly correction action. Do we perceive that there is an obstacle incoming? Are we able to stop the car to avoid it? Are we able to complete the maneuver fast enough to avoid it? And for the other person that could be involved, is the same. Is the person involved able to see that there is a car approaching, so the person can move away from the trajectory of the car? These are the things that we have to consider when defining the controllability. The controllability examples are this one. So here we have to consider operational situation that could happen when we have an hazard, and which is the reaction that we can have. Example, we have an expected increase in the radio volume. This could happen. but it is very easy to control. It doesn't impair our capability of driving. Maybe it is distraction, it is disturbing, it is annoying, but it is not going to alter our capability of driving. Other example, if we have an emergency braking, and so we have the car that is, for example, on a wet road, and it is losing traction, most likely the average driver, depending on the speed, is able to gain control of the car again. So it is normally controllable. Another scenario could be when we need to do a sudden brake and the brake doesn't work. That is not controllable at all. It's difficult or uncontrollable. Okay? So for the consideration that we have done so far, we can see that we could have most likely C1 when we have good visibility, and then we could have C equal to 2 when we have reduced visibility. We are driving low speed, so in general it could be easy to stop the car. That is the safe condition. The point is, which is our perception of, which is the name? Perception, sorry, I'm tired. Which is our capability of perceiving that there is an obstacle incoming. If we have a good visibility, maybe we have a good controllability. We can see that there is an obstacle incoming. If we have our visibility partially obfuscated because we have an obstacle and we are not able to see well around the car, it could be the case that we have reduced controllability. Okay? That's why I placed 1 for operational situation 1 as far as controllability is concerned, and 2 for the other. Okay? Is this clear? Then I did the same for the other operational situation. And here we have the ASIL determination. So we have the table that we have seen before. Once we know severity, exposure, and controllability, we can tell which is the ASIL of the hazard and the operational situation. We have a rule of thumb like this one. We sum the 3 parameters. Oops. If the sum of severity, exposure, and controllability is 6 or less, it is quality measure. If it is 7, it is A, then 8B, 9C, 10D. Okay? This is a way for avoiding learning this. So in our scenario, we have that. For all the conditions where we have good visibility and 2 vehicles involved, we have QM. When we have good visibility and the cyclist is involved, we have A. When we have low visibility and the vehicle involved, again, we have A. When we have low visibility and the cyclist involved, we have B. Okay? So here we have the ASIL. So we know which is the risk associated with the usage of the faulty cross-traffic assist in the operational situation that are relevant for the item, and we have an incident. Okay, we have ASIL A and B. So we have to do something. We have to do some design to increase the capability of our system to avoid the risk. So, which is which are the safety goals that we can specify? Well, first of all, whatever there is an obstacle, we must be able to report it. So the safety goal could be the item shall report obstacle, if any, and the distance to the obstacle shall be reported correctly. So if there is an obstacle, the item shall be able to tell me it is there, and the distance, the correct distance is this one. We cannot accept to have no indication of obstacle or faulty distance from the obstacle. Okay? The other safety goal is, in case the item is not able to report obstacle, it shall transit in the safe state. The safe state is a concept that we haven't seen yet. The safe state is a state in which, even if the item is not providing the intended functionality, the functionality provided is not harmful. The item is not working, but it is not giving me a misbehavior that could harm somebody. The item is not able to measure the distance because it recognized that the sensor is broken. So it will say to the driver, CTA not working, go to the repair shop. This is a safe state. Something that is not acceptable is the case where the sensor is broken and the item is not able to recognize this scenario. So it doesn't give any information to the driver, so the driver behaves supposing that the cross-traffic asset is there. So it doesn't, maybe the driver doesn't take too much attention to what is happening around the car, and so you can have an incident. Okay? Is this clear? So the safe state is the state in which the item shall enter if it is not able to provide the intended functionality. The safe state is a state where the item does not procure any harm to the user. So the bottom line is that when the item is faulty, it is best if it is turned off and the driver is informed. Then, obviously, it depends on the item. If this is a cross-traffic assist, we can accept that the item says to the driver, I am faulty. Don't rely on what I'm saying. In other scenarios, you can have different safe state. Let's imagine that you have a fault in the electronic control unit that controls your engine. In that case, the safe state could be you cannot drive faster than 30 kilometers per hour. Why is that? Because maybe that is the speed that is enough for allowing you to park the car along the road and turn this off. Remember the state machine that we have seen the first half of the lecture before the break. We need to be able to transit either from uncurrently working vehicle in use back to currently working vehicle in use, or to uncurrently working vehicle not in use. This means that when we recognize that there is a fault, either we provide a degraded service that is safe for the user, or we do not provide any service. Okay? Is this clear? Then, how can we implement the safety goal? So how can we reach the safety goal? Through the functional safety concept. The first one could be, we want to be able to always provide the correct distance. So we may have redundant radars. So in each side of the vehicle, we could have 2 radars, and in case of mismatch reading, the item shall enter in the safe state. Other functional safety concept, the item shall periodically check the network and the microprocessor integrity. If a failure is detected there, the item shall enter the safe state. Okay? Is this clear? Well, I give you an exercise. This is something that we can do together next time. Let's think about the QA, Q assist. So the Q assist is a system that you can enable when you are driving the queue, so that the car is automatically able to keep the safe distance from the vehicle that you have behind you. So you don't have to touch the accelerator pedal. The car does everything on its own. You just have to keep control of the steering wheel. This is an example of semi-automatic driving. The car is able to move, to accelerate or decelerate to keep the correct distance from the preceding vehicle. Correct distance means safe distance, so that you're able to stop the car if you see that the car in front of you stops moving without hitting the car in front of you. This is something that you can implement with a system like this one. You have a front radar that gives the distance to a microcontroller. Then the microcontroller receives the vehicle speed and the status, whether the item is active or not. And then the microcontroller is able to close this loop, the speed loop with the car. So this microcontroller is able to give commands to the vehicle to accelerate or decelerate to keep always the safe distance from the preceding vehicle. The safe distance can be defined as this one. So if the distance is greater than the speed of the vehicle divided by 10 to the power of 2, then the distance is safe. So you can stop the car without hitting the car in front of you. If not, it is not safe. So the exercise is, let's analyze this item using the concept phase of the ISO26262. And let's see what happens. Okay? Any question? Any doubt? Okay, see you next week.